It's theorized to be a vast cloud of icy bodies at the very edge of the solar system, first proposed by the Dutch astronomer Jan Oort back in 1950, but the idea was postulated by the Estonian astronomer Ernst Öpik 20 years earlier, back in 1931. Oort was, however, unaware of Öpik's earlier work, and today we call the object the Oort Cloud. Let's look at the outer solar system. Neptune is the most distant planet from the Sun. Beyond Neptune is the Kuiper Belt, small, icy objects. The best known of these is the dwarf planet Pluto. The scattered disk is an extension of the Kuiper Belt and includes objects with greater eccentricities, meaning the more elliptical orbits, and also further away from the ecliptic plane, the plane in which the Earth orbits the Sun, than the traditional Kuiper Belt objects. The heliopause is the boundary between the solar system and the interstellar medium. And beyond the heliopause is the Voyager 1 spacecraft. It's travelling away from the solar system at the rate of 3.57 AU per year. In hundreds of years' time, it will cross into the Oort Cloud. But of course, by this time, its transmitters will no longer be working, so we won't be able to know what it finds. Now, in this diagram, the distances aren't to scale. If we redraw the diagram and have the distances to scale, you can see it looks very different indeed. The Oort Cloud consists of two parts. The outer Oort Cloud is roughly spherical, has perhaps 1 trillion objects larger than 1 kilometre in diameter, and perhaps 1 billion objects larger than 20 kilometres. Its total mass is round about 5 times the mass of the Earth. But when you do the maths, it's not very dense at all. You'd only have 2 objects larger than 1 kilometre in 1,000 cubic astronomical unit cube. The inner Oort Cloud, which is sometimes known as the Hills Cloud, is donut shaped and has roughly similar mass to the outer Oort Cloud, but because of its smaller volume, it must be at least 25 times denser. If we think about the brightness of distant objects from the solar system, which shine by reflected light, you can actually show that the brightness declines as the 4th power of its distance from the Sun. This is because the amount of sunlight it gets from the Sun declines as the inverse square from the well-known inverse square law. But its distance from Earth also declines as an inverse square. So when you put the two together, you have an inverse 4th power relationship. This means, if we do some rough calculations, even at a distance of 2000 AU, so that's on the edge of the inner Oort Cloud, an object 1 kilometre in diameter would have a magnitude of plus 49. An object 20 kilometres in diameter would have a magnitude of plus 42.5. The faintest magnitude which we can detect with an Earth-based telescope is 28. So, the conclusion is quite clear. No Oort Cloud object has ever been seen or can be seen with our current technology. If we look at short period comets such as Swift-Tuttle, that's the one that's responsible for the Perseid meteor shower, they tend to be in orbits which lie relatively close to the plane of the Earth's orbit around the Sun, the ecliptic. With long period comets such as the Great Comet of 1996, the situation is a little bit different. These aren't constrained to be in the plane of the ecliptic, they can either go well above or well below the ecliptic, and they can orbit the sun any way, the same direction that the Earth does or in the opposite direction. The theory is that because their distances of the aphelion, when they're furthest from the sun, is so far away from the Earth and forms a roughly spherical distribution around the Earth, there must be a near spherical source of icy bodies which cause these comets. What happens, we think, is that something called the galactic tide and a passing star can disrupt this cloud, deflecting them into the inner solar system. I'll talk a little bit about this next. An object in the outer region of the Oort Cloud is very weakly bound to the Sun. At 50,000 AU, it takes 11.2 million years to go around the Sun in a circular orbit, compared to 1 year, which it takes the Earth. The Sun's gravity at this distance is 2.5 billion times weaker than it is at the Earth's distance from the Sun. Most people are familiar with the tides caused by the moon. This is due to the fact that the average strength of the moon's gravity is different on the side facing the moon than on the side of the Earth facing away. What we can do is, if we take a two-dimensional slice through the Earth, this shows the direction and the magnitude of the moon's gravity. And you can see, not only does it vary in strength, being stronger on the side closer to the moon, it also varies a little in direction. If we take the Earth as a whole and another two-dimensional slice through it, we say the tidal force is the difference between the moon's gravity at a point and its average value over the entire Earth. So it has both a magnitude and direction. It's very weak, round about 10 million times weaker than the Earth's gravity. But even though this force is weak, it is the force responsible for tides, the raising and lowering of the sea level twice a day. Now, if we take the case of the solar system, it lies in the outer region of our Milky Way galaxy, about 27,000 light years from the galaxy centre. So there is a galactic tide, with one side of the Oort cloud having slightly weaker gravitational attraction than the side closest to the galactic centre. However, it's a bit more complicated than the situation with the tides caused by the moon, because not all the mass of the galaxy is concentrated at its centre. There is a galactic bulge around the centre, but there's also a disk where a lot of galactic material is held. So the galactic tide is quite complicated. There are components due to the gravitational force of the galactic centre, but also the disk, and even a halo of globular clusters around the galactic centre. Although the main evidence for the Oort cloud is the origin of long-period comets with their aphelion thousands of AU away from the Sun. Another strong piece of evidence is that models of the early solar system show that early in the solar system's history, giant planets scattered a significant amount of icy bodies outwards, and computer simulations predict that these would have been flung out into extremely remote orbits and then the slow and steady interaction of the galactic tide would have changed these orbits from being in the ecliptic into more spherical shapes. The Hills cloud, or inner Oort cloud, is a more recent development to the theory, first proposed by Jack Hills back in 1981. It's believed to be donut-shaped, inner radius 2000 AU, outer radius 20,000 AU. Once again, there is no direct observational evidence for this. The objects are far too faint to be seen with any telescope, but recent computer simulations have confirmed that such a structure should form. Though interestingly, a recent paper suggested that the structure wasn't donut-shaped, but could in fact be spiral-shaped. But again, it's a theory which is very difficult to prove or disprove because we can't observe it directly. Gliese 710 is a pretty unremarkable star. It's roughly 0.6 times the mass of the Sun and is a lot cooler, which means that it's only 4.5% as bright as the Sun. What has been known about this star is, for quite some time we've known this, in fact, it's going to pass very close to the solar system at some point in the future. Recent Gaia measurements have suggested that it's moving towards us at 52,000 kilometers an hour. And it's got almost no sidewards velocity. So the natural conclusion is it's heading pretty much straight towards us. A recent paper suggested that it had a 99% probability of getting between 9,300 AU and nearly 12,000 AU from the Sun, with a mean value of 10,500 AU. This, from what I've said earlier in the video, is going to take it well within the inner Oort cloud. To people observing it at its closest approach, its visual magnitude will be minus 3.2, which is 5 times brighter than Sirius, the current brightest star. And if it gets as close as 0.147 light years, its visual magnitude would be minus 3.5, even brighter still. It will be the brightest star in the sky, roughly the same diameter as the dwarf planet Pluto at its closest to the Sun, and larger than any star we can see today. We normally think of stars being fixed, but Gliese 710, when it's moving so close to the Earth, will actually move relatively rapidly compared to background stars. If you take a period of 80 years, it will move through the sky by about 1.5 degrees, 3 times the diameter of the Moon. So we'll have to update our star atlases every few years to show the gradually changing position of Gliese 710. And although Gliese 710 is less massive than the Sun, it's still considerably massive, 600 times the mass of Jupiter, 190,000 times the mass of the Earth. And as this ploughs through the Oort cloud at 52,000 kilometers an hour, it's going to have quite a significant impact. In fact, the close approach of Gliese 710 will be the strongest disrupting encounter in the future and the known history of the solar system. The disruption of the Oort Cloud will create comet swarms. A recent paper suggested 30 million new comets. But what we don't know is how many of these new comets will be short period comets which could come close to Earth. And the effect on the Gliese 710 Oort cloud, assuming it exists at all, is unknown. So while articles such as this one in Newsweek might make interesting reading, we can't say whether this is likely to happen in 1.3 million years' time. We don't know. My guess is there will be some impact on Earth, there will be more comets, but whether we'll have a extinction event like the one which wiped out the dinosaurs, we can't say.